chapter 7 is on quadrilaterals and other polygons. 7.1, we're going to focus on angles of polygons. So first, let's go back. I think we've gone through and named these before. I'm not really sure. This book mixes me up because some of the things are in different order. But this three-sided polygon is a triangle. Four-sided is it a square? Is it a rectangle? What do you call all four-sided figures? Quadrilateral. Five-sided? Pentagon. Six-sided? Hexagon. Seven. Everybody says septagon. Why do they? Is there something else that has seven something that's S-E-P-T? Heptagon.
A lot.
What about, where are we? Wait. Yeah, didn't write it down. Heptagon. And then eight-sided. Octagon. 9. Monogon. 10. And then we skip to 12. We don't have one for 11. I'm sure there's a name for one, but we don't use that. And here we just go to 12. It's a dodecagon. Okay. Now let's go back and put number of sides. 3, 4, 6, 7, 8, 9, 10, and then 12. Number of triangles. Well, that's a weird column, isn't it? There's one triangle in a triangle. And what that means by number of triangles, that's if you were to connect from one vertex in a polygon to another, not consecutively, how many just from one vertex, how many triangles? So if I pick one vertex to draw a diagonal from, how many times could I do that to create another triangle? I can only do it once here. So there are 2 triangles in a quadrilateral. Here, I can only do that 2 times in a pentagon. So there are 3 triangles. In a hexagon, there are 4 triangles. So what's the pattern here? How many will I have here? 5, 6, 7, 8, 10. Okay. Now, you may wonder, why am I doing this? Well, what is the sum of the interior angles of a triangle? We know that already, right? Sum of the interior angles is, on a triangle, 180. We know that because of the angle sum theorem, right? 180 degrees. Well, the reason we want to know, well, tell me how many, I think you already know how many degrees the sum of the interior angles of a quadrilateral. What is that? Don't we already know that? I don't think we've talked about it in here, but I think you've learned that in the past, maybe? Think of a square. All 4 sides add up, all 4 angles add up to 360. And that's true for any quadrilateral. Do we know the sum of the interior angles of any of the others? Probably not, but those 2, you maybe, I don't know. I think you should have known this. I'm not sure. Well, what's happening is, according to however many triangles you have in the polygon, that can help you come up with the number, the sum of the interior angles. Because Once you if you create all those triangles and add up all the angles inside each triangle, because the angles that are adjacent to each other, they add up to the bigger angle. That ends up being the sum of the interior angles. I don't know, that's kind of hard to explain, and maybe I can give you a figure in a minute to show you a little bit more. But what you need to know is that there's 3 triangles in a pentagon, and 3 times 180 will give you the sum of the interior angles. 3 times 180 is 540? Is that right? I need help here. 540. And then 4 times 180 would be 720. 5 times 180 would be 6 times 180 would be 7 times 180 would be, have to carry the 1. Is that right? Okay, and then another triangle would be, did I skip something? No, I didn't. I'm looking at the wrong thing. Okay, another one would be, is it 1800?
Yeah.
10 times 180. All right. Well, here's the problem. You know, there are polygons that have 50 sides. Do we want to keep adding 180 every time until we get up to 50 to find the sum of the interior angles of a 50-sided polygon? No. We need a formula. We need a formula based on the sides of the polygon. We need a formula to find the sum of the interior angles of any polygon, whether it's 6-sided or 25-sided or 100-sided. Is there a limit to the amount of sides a polygon can have? No, you could have 1,000,000. And I certainly wouldn't want to add up 180 until I get to 1,000,000. What does that start looking like when you get that many sides? A circle. So what is a shortcut if I wanted to know the sum of the interior angles of a 50-sided polygon? What could I do? There's got to be something based off the number of sides that we could do to find the sum of the interior angles of any polygon. What's the relationship between the number of sides and the number of triangles? Always 2 more sides than there are triangles. So if I take the number of sides and subtract 2 from it, then I can multiply that answer by what? 180? Because that's how many triangles we have. So are you telling me that the sum big S, representing the interior, sum of the interior angles of a polygon, big S, the sum of the interior angles of any polygon is equal to, let's do n minus 2, n the number of sides, minus 2 times 180. Another way you can write that if you prefer, that's 180 times n minus 2. Both are acceptable. They're the same thing. Commutative property allows us to write it either way. So, if I want to know the sum of the interior angles of a 50-sided polygon, that would be 48 times 180, right? 48 times 180. y'all don't have to write this down. I'm gonna try to explain why that works, and so maybe this you will remember this forever. I don't know that I'll be able to make this up though. I could use a protractor maybe. It's hard to do. I hope this works after all that. Let's see. Oh, works. That works. Okay. So if you were to add the three here together, they add up to 180. If you add the three here together, they add up to 180. Three here add up to 180. And if you take all of them and add them together, they add up to 540 degrees, which is the sum of the interior angles of a pentagon. So the reason that works is, you think that's just weird, you're putting triangles inside of it, but if you take the measure of this angle, plus the measure of this angle, plus the measure of this angle, add them together, that is the measure of this whole angle. So that makes sense, right? And if you take the measure of this angle and this angle, add them together, it makes the measure of this whole angle and then this whole angle. So if you add all 5 angles together, they should add up to 540. It doesn't matter if the pentagon is regular or irregular. What does that even mean? I haven't taught you what that means. So, regular and irregular. You do need to write this down. A regular polygon has all sides the same length, all angles the same measure. The sum of the interior angles of that regular polygon, if it's a pentagon, is 540. And then if you have a pentagon that's not regular, which is something we don't picture, we never, if you want to know, this is how I keep up with the difference between regular and irregular. If I say pentagon, I would be totally surprised if this is what picture pops in your head. It's always going to be this regular shape, right? If I say octagon, it's going to be regular. You're not going to have some weird 8-sided polygon pictured in your head. Triangle would probably be the only one. Triangle or quadrilateral would probably be the only ones that you might picture differently. Like a quadrilateral, you may picture a parallelogram, a rectangle, but a regular quadrilateral is a square. That's the only thing a regular quadrilateral could be, is a square, because that's the only 4-sided figure that has all 4 sides the same length and all angles the same measure. So if that's the case for a quadrilateral, what's the case for the triangle? Which triangle? What can we call a regular triangle? Equilateral or equiangular, which are one and the same. You're just classifying, you're saying it by its side or by its angles. So a regular triangle is not a right triangle. It's not an isosceles triangle. It's not, well, there's a case for that, but we'll talk about that right now. It's not a scaling triangle. It's not an obtuse triangle. It can be an acute triangle. It is an acute triangle, but it's a equilateral triangle where all three sides are the same and all three angles are the same. But it doesn't matter if it's regular or irregular. The sum is always the same. It's the measure of each angle that would be different. So if I want to know the measure of one angle in a pentagon, a regular pentagon, all I have to do is take the sum and divide it by 5, the number of sides. So 540 divided by 5, if they're all the same measure, then I just take the sum and divide it by the number of sides, or the number of angles, which is the same, and I get the measure of each individual angle. I can't do that here because this had to, as this got larger, this got smaller. These three maybe got smaller as the two over here got larger, but they still all add up to 540. So the only way I can tell you the measure of each individual angle here is if I'm given more information, like an expression to set up an equation, similar to what we did with a triangle. So all of the figures that are drawn in this chart are regular. All sides are the same length. All angles are the same measure in each one, not all of them together. All right, so here is your lesson header. You can put it on the top of that chart, or you can, however you want to do it. I just like talking about all that before we get started, because I like discovering this instead of just giving it to you. So maybe it helps you to remember it. Somebody still writing? Whoops. So the sum of the exterior angles of a convex polygon is 360. Notice there's no formula. There's no formula. We learned already what an exterior angle is whenever we talked about the exterior angle theorem. In order to construct or draw an exterior angle, all you have to do is extend one of the sides. When you extend one of the sides, it's the smaller angle made with that extension in the side of the polygon. So I have 3 figures here with the exterior angles added to the figures. And you can see how the exterior angles add up to 360 no matter how many sides you have. Back whenever I used to do math team, and I was at a different school, every time at the county tournament there was a problem that had something to do with the exterior angles of a polygon. And they try to trick you into not remembering that the sum is always 360. So what they would do is they would put a problem on the test that said the sum of the exterior angles of a, let's say, octagon is, and then it's multiple choice, you would have 4 choices of degree measures, and then you would have E. None of these. The 4 choices would not be 360. It would be all different measures, but it would not be. So your answer option would not be 360, and you know you don't like to put E, right? We never like the none of these answer choice, because we know that it seems like there's always more, like 3 or 4 that you want to put E on, and there should only be maybe 1. So people tend to get that one wrong because they can't remember the sum of the exterior angles 360. It never changes. You could have 100 sides Could have a 100-sided polygon. Some of the exterior angles is 360. Have a million-sided polygon. Some of the exterior angles 360. The more sides you have, notice, the more sides you have, the smaller this angle gets. So if you have 1,000 sides, that's just a tiny sliver. It's 360 divided by 1,000. It gets smaller and smaller and smaller and smaller and smaller. But it's the interior that changes. The exterior never changes. The interior does change as far as the sum. Now each angle measure changes because you're dividing 360 by 3, you're dividing 360 by 4, you're dividing 360 by 5, 6, 7, 8, 9, 10, depending on how many sides you have. So if it's regular, if all of the sides are the same measure, all the angles are sides are the same lengths, angles are the same measures, then all of the exterior angles are congruent to each other and they add up to 360. But let's, if this were not an equilateral, then these three would be different measures, but they would still add up to 360. Okay? Find the sum of the measure of the interior angle of the indicated convex polygon. So what I want you to do every time is write down the formula. S equals n minus 2 times 180. I don't care if you put 180 first, that's okay. The sum is equal to 14 minus 2. Now this part, I don't care. You could just, if you want to put 12 at that point, that's okay. But I do want you to write down the formula. It's smart to plug into the formula instead of trying to simplify here. So 12 times 180 . Anybody else get 2,160? Okay. Now, what if, just to add to this, what if I said this is a regular polygon? If the sum of the interior angles is 2,160, can we find the measure of just one of those angles? What would we do? What could we do, Sarah? So if I want to know the measure of just one angle, I take 2160 and divide it by 14. Because if it's regular, all the angles are the same measure, I can just divide it by the number of angles or sides, which are the same. Next problem. The sum of the measures of the interior angles of a convex polygon is given, 3,240. Classify the polygon by its sides. So we can use that same formula. But this is the sum, so I plug it in for S, not in for N. I'm looking for N. Should I distribute the 180 or should I divide by 180? What would you do? If I distribute the 180, that means I multiply this by both things, and I have to add whatever I get over here and then divide here. If I just divide this, if I divide both sides by 180, once I get my answer, all I have to do is add 2 to it. Right? So let's divide both sides by 180. You can still get the same answer by distributing. You're just going to be doing more work, and without a calculator, nobody wants to do more work. I wouldn't think. So 18 is not the answer. It's not an 18-sided polygon. It is, that's how many triangles we have. It's 20, right? 20-sided polygon. The good news about this is always going to go evenly, right? Because you can't have 20 and a half sides. Can you? Or 20 and 1/4 sides. Doesn't make any sense. So it should go evenly. If it doesn't, then something's wrong. All right, now what are we going to do if we have a polygon that's not regular? As long as we have enough information, we can find out something we need for the polygon. This is, what kind of polygon? Is it a triangle? Is it a quadrilateral? Is it a pentagon? Is it a hexagon? Is it a dodecagon? What is it? Quadrilateral. So we need to know that. We need to know, not necessarily the name, but how the sum of the interior angles. So if we don't know the sum of the interior angles, we will not be able to find x. The sum of the interior angles of a quadrilateral is 360 degrees. So similar to all that work we've been doing with triangles, whenever we try to find the missing angle of a triangle, we subtract the two angles from 180, or we add them up and set them equal to 180. Do the same thing here, except for instead of 180, it's 360. So we know that x plus 103 plus 133 plus 58 2, 3, 4 is equal to 360. So x plus can somebody double check that, please? Is that correct? Anybody verify that? Okay. And then subtract 294 from both sides. That would be 66. All right. There's my answer. And you can double check by adding 66, 103, 133, and 58 to see if it gives you 360. Here's the problem with a problem like this. If you don't know the sum, if you're taking a test, let's say you don't remember, I'm not telling you that you have to have this memorized. I'm not telling you have to have this memorized. But I am telling you, you have to be able to find these things. So you at least have to have the sum of the interior angles formula memorized. Because sometimes you have to know what to set your equation equal to. Or how to set up your equation. Okay? Just like this one. 1, 2, 3, 4, 5. That's a pentagon. It's a weird looking pentagon, but that's a pentagon. We have to find the values of angle X and angle Y. Okay, so we're going to add up all the angles, set them equal to, what was the sum? If we don't know the sum, we have to use the formula, but hopefully we know the sum. Hopefully there's few enough sides that it's the sum that we can remember. Because once I get past the pentagon, I don't really have all that memorized. 540? Or you could say, okay, there's 3 triangles, 3 times 180. Yeah, 540. So all angles have to add up to that. So let's see if I can have something over here to represent each angle. I know this is supposed to be a right angle. So that's, let's start with our variables first. These two are showing that they're congruent to each other. So if I want to use a variable, I can, but it's going to be weird if I use x because I have x here and y here. But I can use x because these are capital letters. So I could use x because it's a lowercase. And if this is x, right? If they're congruent, if one is x, they're both x. So x plus 90 plus 47 plus 119 has to add up to 540. So that's 2x plus I did not do that right. 256. So 2x is equal to 540 minus 256. That's 240 plus 44, which is 284. And then divide both sides by 2. That's 142. Okay. So angle X is equal to angle Y, which is equal to 142 degrees. You can write them separately or together like that. Yes? Looks like we will not be finished today. I will go ahead, and if anybody wants to write this down to get started, you can, and then we'll finish the lesson tomorrow. And once we finish the lesson, you'll have till the rest of the period to do the homework. And what I will want you to do is have that work done by the end of the period so that you don't have homework during Thanksgiving. So if you can go ahead and get started, that will help you finish by the bell tomorrow.